Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week, and we'll be talking about the jet stream and why it is stronger in the wintertime than it is during the summertime. And some of this is review. We're just sort of looking at it in a slightly different way. So let's go on ahead and get started here. And the first thing we're going to talk about, or I want to share with you, is if you are a weather fanatic, then the Storm Prediction Center, and this is the part of NOAA that issues all of the watches for everywhere in the country, and then the warnings are issued by the local National Weather Service office. But anyways, they're the folks that do that. They're the ones that put out the convective outlooks for the next 3 days, alerting people to potential severe weather hotspots. But they also have a really cool page called the Sounding Climatology page, and it has historical weather balloon information from sites all over North America and all sorts of interesting ways to analyze that data. So that is the URL in case you're interested in checking that out, and that's where the information in this Patreon video came from. Okay, so this is the average wind speed in knots at 850 millibars at Greensboro. Greensboro is one of the two places in North Carolina that sends up weather balloons at 8 in the morning and 8 at night. Once we go back to standard time, it'll be 7 in the morning and 7 at night. And you know how when I show you the precipitation forecasts on the daily weather update occasionally that I talk about the 25th to the 75th percentile, where you have a bell curve and the middle 50% is right in there between 25th and 75th? Well, that's what that shaded red area is there, okay? So that's where most of the values lie, and then the outliers are either above that or below that. But if we take a look at the month of January, the median, or the 50th percentile for wind speed at 850 millibars, which again is about 5,000 feet up, is 22 knots, okay? And then if we take a look at it in August, early August, it's 10 knots. That's about as low as it gets. So we have a range there at 850 millibars from 22 knots to 10 knots, or a range of about 12, okay? Now, let's go on ahead and take a look at 250 millibars, which is up probably at around 35,000 feet. And here, the median goes from 86 knots in January, which is right around 100 miles per hour, I think. And it ranges all the way down to 32 knots in July. Okay, so that's the 50th percentile at 250 millibars. So there you have a 54 knot range as opposed to a 12 knot range during the or at the 850 millibar level. So obviously there's a lot more variance way up there than there is closer to the ground. So here we've got a cross section, and this is in the summer, and Texas is on your left, Minnesota is on your right, and it's hot in Texas and it's warm in Minnesota, so we'll just call it cooler, okay? But I mean, Minnesota can have days in the 90s at the same time that Brownsville, Texas is having days in the 90s, okay? So the temperature contrast from south to north across the United States in the summer is generally not all that terribly great. So we've also talked about the distances between two surfaces of constant pressure being proportional to the temperature of the air between them. So it sort of makes sense if you think at it this way, that if these two surfaces of constant pressure are way far apart, then that's warm air. It's less dense, spreads out over a bigger area. If it's cold, then they're going to be close together because cold air is more dense than warm air, okay? So here is a 850 millibar surface of constant pressure. This is in the summertime, and then there's your 250 millibar one. Now, you probably can't tell here, but the 251 is slanted or tilted just a little bit more than the 851, but not much. And the reason I wanted to do that is that I wanted to show that the temperature contrast from Texas up to Minnesota is not all that great. So the distance between these two red lines is not going to be all that great. Now, I've put in here a dotted line showing constant altitude, okay? So remember, the pressure gradient force operates from high pressure to low pressure, and the stronger that force is, the stronger the wind is. So if you look along this dotted line here, the pressure here is not all that terribly much different than it is here. It's a little lower here, but not much. So the pressure gradient force is going to be fairly weak. And the same thing up here, even though this line is tilted just slightly more, the difference in pressure along this dotted line here is not all that great, and so the pressure gradient force is not all that great. And so at both 850 and 250 millibars, the winds are not all that terribly strong in the summer. And so small pressure differences implies weak winds, and small pressure differences imply, I'll say, weaker winds up at 250 millibars, because it's usually always blowing at least to some degree out there. Okay, now let's go to the winter, okay? So it's warm in Texas and it's cold up in Minnesota, okay? So the difference in temperature is usually much greater in the wintertime from south to north. So here is our 850 millibar line of constant pressure, but the 250 millibar line has to tilt a whole lot more in the wintertime. Why? Because these two lines, the 850 and the 250, have to be closer together where it's really, really cold, and they have to be much farther apart here where it's warm, okay? So now let's put in our dotted lines at constant altitude. Now, again, at 850 millibars, the pressure is not, again, all that much lower up here than it is over here, so the pressure gradient force is fairly weak, and so the winds are going to be relatively weak. But at 250 millibars, because that line tilts so much, the difference in pressure between here and at the same altitude over here is huge, okay? So the pressure gradient force as a result of that is much, much stronger, and so you have much, much stronger winds at that altitude during the course of the winter or any time of year when the amount of temperature contrast from south to north across the country is large. And of course, the largest values of those differences typically occur during the winter season. So this is one of these things where when you are near a frontal zone, the winds typically increase in speed as you go up through the atmosphere. But if you're in a fairly uniform area of temperature where there isn't a lot of variation, then the winds are not going to increase all that much as you go up. So what have we learned? Number one, the meridional, which is a fancy word for north-south or south-north, temperature gradient being a fancy word for difference, is larger during the winter than during the summer, obviously. In the summertime, Texas is really hot, Minnesota is very warm, but the difference is not all that terribly big. In the wintertime, it could be in the 70s and 80s in Texas and 30 below zero in Minnesota, okay? So much, much bigger differences during the course of the winter season. Surfaces of constant pressure are closer to each other when it's cold and farther apart when it's hot, okay? So during the winter months, the surfaces of constant pressure higher up in the atmosphere have a much steeper tilt toward the pole than they do during the summer. And so as a result of that, the pressure gradient force at a given altitude is quite strong, and therefore the winds at that high altitude are also quite strong, okay? So that's basically it, that when you have a strong jet stream, you know you have a lot of temperature contrast across that jet stream from one side to the other. And so if you have 150 knots sustained winds at 250 or 300 millibars, you know you've got a lot of temperature contrast across that jet stream from one side of it to the other. All right, folks, hope that made some sense. That is bonus weather video number 2 for this week. Number 3 will be coming up on Friday. Hope you have a great rest of your Wednesday evening, and we'll talk to you again with the next daily weather update tomorrow. Take care, everybody. See you later.